Okay, let's make a start. So this time we're going to continue on with last week's class 2 where we had a look at basically the introduction to transformations. If you weren't there for that class, that won't be too much of an issue. I'll just have to sort of repeat like one small, mainly conceptual thing with the overall idea of what we're doing with transformations. In the last lesson, we looked at how to apply a number of transformations to our functions, that being any of your dilations, reflections, and translations. In this case, we're going to essentially do it in the reverse order. We're going to have a look at a function and try to figure out what sequence of transformations would get us from our starting point to our new ending point. So let's have a look. There's going to be a couple of ways we can do this. The main way is going to be used what's referred to as the point notation approach, which is what we covered in the last lesson. I will, again, basically briefly recap that. The other alternative will be the idea of transformations by recognition, where what you're essentially doing is looking at your initial function f of x and applying transformations directly to the function rather than doing it using your xy and x dash y dash stuff. So we'll have a look at both. Feel free to focus on whichever one of those works for you. But the bulk of what we'll look at will be this point notation simply because it's the most structured, right? You just do the same steps every single time and you get the same result. Doing it by recognition where you're subbing things directly into f of x, you have to play a little bit more with your algebra. So it's more skilled in that way, but it is also a bit faster. So feel free to try both. Pick one that you like the most. You do still need to know a little bit about this this first approach though, so we're definitely going to have a look at that. Okay, cool. So here is the steps for those of us who were in last week's class of this. They'll look kind of similar. We'll actually just sort of have a look at an example though, rather than just sort of read it directly off there. So in this first example, we're going to have a look at what it takes to go or find a sequence of transformations that takes us from some initially transformed function to an untransformed function. That's not necessarily a unique thing. You can have any start point and any end point. There'll only be one small nuance that we'll see show up in both examples. So in this case, we have a truncus. We've got some transformed truncus, and we're trying to get it to basically have no transformations applied to it. First step, we want to figure out what the original function is and call that f of x, and figure out what the new function is, g of x. So this is already written for us. The specific you want to try to make sure you do here is label your xy and x dash y dash to those specific functions. So your x and y stuff will be for your f of x, the original function, which is why we're now using y and x in this f of x. And the new function that you're trying to end up with, that's going to be x dash y dash. This is simply for us to keep track of where we're starting and where we're going, essentially. And what we will be left with, this x dash and y dash, will be the set of transformations that had to have been applied, which we'll see at the end. Next up, once we have that, we're going to look at both of those functions and then rearrange all the y transformations to the y side, and all of the x transformations going to stay where they were. So, if we look at our f of x, our original function, there is a vertical translation that would be considered something impacting the y. So we bring that over, that's the -6. And we also have this dilation factor of 3 here, which is also considered a y transformation. And so we're going to put that over to the left-hand side as well, getting everything on the y side. Everything else is just going to stay as is. We got the x transformation there, nothing else is x transformed. And this one didn't have anything on it. It was a bare bones basic truncus, so there's nothing to rearrange. But if they did both have transformations applied to them, you would do this procedure on both. Cool so far in identifying like what's a y transformation and what's like what should be moved over here? Cool. Because like the hack for this is like, if for whatever reason you're worried about what do you actually move, pretty much just move everything over that you can before it breaks down into a different looking function. Like for instance, you wouldn't want to expand this out and then try to shift things over. It would no longer look like a trunkus anymore. So that's just a sort of like a litmus test for how much you should move over, just in case you forget what's your Y, what's your X stuff. Okay, so from here, what we have now done is, because we put all the Y stuff on the Y side and the X stuff on the X side, we can write a direct comparison between where we're starting and where we're going in terms of the X and Y. So we look at the first function, whatever is in the Y spot goes on one side of the equal sign, and then we look at the second function, whatever is on the Y spot will go on the other side of the equal sign. The Y spots of both functions are equal to each other. Same thing with the X spots. So technically speaking, you can just rip the entire right-hand side and make them equal to each other. It will just simplify down into this at the end. If you're more skilled and you see this many times and you practice it enough, you'll start to realize that all you actually care about are the transformation factors themselves. So you can directly take that x minus 1. That's the only actual transformation factor that's there. And this one, well, it's just x. There's nothing actually there. So if you want to skip that step, go right ahead. That's what I've done here. Alternatively, you can write the entire right-hand sides equal to each other. All you would do is cross multiply the denominators and you would get back to exactly where, and square root. And you get back to exactly this. Any questions so far? Okay. Part B, rearrange to make sure you have x dash and y dash on its own. So, because we started specifically with a transform function and made it to an untransformed, pure bare bones basic thing, there actually isn't anything left to do here. Sometimes this y dash and x dash actually does have stuff attached to it, so you do have to do a bit of rearranging, which we'll see in the next example. But in this case, it was as basic as I could make it, more or less, and so there's just nothing else to rearrange for. So if you remember from our previous lesson, what x dash and y dash are in fact the transformations that are applied to the x and y respectively. So if we express this in like our point form, we say we're starting at xy and we're moving towards or mapping towards this x dash and this y dash. That is the sequence of transformations, which in some cases you can just leave that as your answer. They'll tell you what form you should write your answer in. In the vast majority of cases, they'll want it as a written sequence, as if you were to explain it to someone else in English, right? How you actually achieve that, this is where things sort of get slightly complicated, because there's a fair few ways you could do this. If you guys have already had a look at transformation stuff recently, I know a lot of teachers will teach to do in the order of dilate, reflect, and translate. If you list your transformations in that order, you'll get a certain outcome. The complication arises mainly in how you're expressing this. So if you express it as a fully expanded version, so as if you were to apply the division of 3 to the y to make it y over 3, division of 3 on the 6 to make it the negative 2, then you could have done DRT, dilation, reflection, and then translation. In this particular arrangement, I've opted not to do that. I've kept it in its factorized form, which is probably a bit more what you guys are already used to, because when you're dealing with your functions and sketching your functions, you want to get it into that transformed state so you can immediately see what your horizontal, your vertical translations are, your dilations. You want to see what all those are. And so keeping it in this sort of like factorized state where all the factors are taken out is probably a bit more of a better habit to have. But just keep in mind that if you are expressing your stuff like that, you should instead do your transformations in the order of translation, reflection, dilation. So I know I said there's like two main ways of doing it. We'll just focus on this one first and just make sure that we've got at least one method of expressing these right. It doesn't actually matter if you do the X stuff first or the Y stuff first. You can even intermingle them if you really want to get crazy with it. Just as long as you do translations, then reflections, then dilations in where X and Y are independent. So for instance, one way of doing this would be to say you have a translation, so we're starting with translation, of 1 unit in the negative X direction, that's this, and then the next translation would be a translation of 6 in the negative Y direction, since it's attached to the Y. You've got Y minus 6. Then we would look for reflections. There are none. There's no negative signs on the X or the Y. And so lastly, we look at our dilations, of which there is only one, which would be the dilation factor of 1/3 along the Y, or you could say from the X, which is probably more what the textbook is likely to say. That's one possible sequence. The other could be, instead of doing all of the X stuff first, you do all the Y stuff first and then all the X stuff. But again, just making sure that within the X and Y subgroups, you're still doing translation, reflection, dilation, translation, reflection, dilation. So this one, we're just done the Y stuff first. Translate of 6 for the Y, dilate of 1/3 for the Y, and then the translation of 1 for the X. So you can see even within this, there's still multiple ways of expressing the exact same sequence of transformations. The way in an exam, what they'll typically do is they'll write out the first bullet point. They'll say, this is the first bullet point that you have, now do the rest. And what that essentially does is it means instead of having multiple ways of doing it, you now have, well, I guess, slightly fewer ways of doing it for them to assess. Fair enough on how that's worked out. This is where it gets the most complicated.
Is there a reason why you would write it as a dilation factor of 1/3 along the y-axis rather than from the x-axis?
Personal preference. Yeah,
Okay.
there's no difference. If you want to be like as the most common would probably be from an axis. However, I've always found when I'm teaching it, if I say from the X, people think it's an X dilation. So I'll usually just sort of say this for clarity's sake. But yeah, the book does pretty much exclusively use from. I have seen some sources which will say along, both of which is valid. But yeah, so if you're learning this for the first time, just do exactly as is written here. And if for whatever reason you want to do the whole dilate, reflect, translate instead, I don't think it's actually written in here, but just keep in mind that you want to expand this out fully. So you'd have to apply this 1/3 to the -6, making it -2, and then you do the opposite order. But that's just sort of complicating things. Cool. So here's the other example, starting from an untransformed state and then going to a transformed state. We don't have to look at all the steps there because they are exactly the same. You still want to figure out what's your starting point, what's your ending point, and you label them accordingly with the X and Y dashes respectively. In this case, the only thing that has to be rearranged to get like all the Y stuff on the Y side would be the new function. The only thing that's going to change ever so slightly is when you now equate the left-hand sides and the right-hand sides together, you now actually have to get the X dash Y dash on its own. There are other stuff that's attached there for you to rearrange. And then yeah, everything else is as we've seen before. One of the things as you get like really advanced with this is you might actually choose what way you want to express your transformations depending on what you end up with here. Like for instance, this already is a fully expanded statement. And so, you know, if you were to be like religious to the way I've done it, in order to do that, you would actually have to go out of your way to factorize it and then write what those transformations are. Versus if you get much more experience with it, because this is in an expanded state, you could now do DRT instead of TRD, and so that skips a single line of working, essentially. So in this case, you would say this is a dilation of 2 from the X or along the Y, followed by a translation of 3 units in the positive Y direction, or something to that effect. And obviously you mentioned the x one as well. So more or less you're doing these things as you get more advanced, depending on what you end up with here. But as you're getting started, pretty much just stick to one, master one of them, and then from there you can start to branch out and see what else is there. That's the point form notation for doing these sorts of things. Anything to clarify further before we move on to a slightly different approach? Cool. So if you were looking at that procedure and thinking, God, that's a lot of work, this might be your next best bet, which is you start looking at the functions themselves and applying the transformations directly to the functions. I will say I've noticed people will tend to make silly mistakes on this more often than others. But, you know, it's also faster as well. So let's have a look. Part of the challenge with this is that I can't actually give you a step-by-step procedure. In fact, I can only really give you guidelines, and that's because each function will sort of require slightly different algebra as you do things. So rather than have a bulletproof list of like, yep, this is what I do every single time, we're now sort of getting into the whole guidelines approach. So some of the guidelines, just make sure that both functions are in their general form. So in other words, like their transformed state, you can see what each of the transformation factors are. Like for instance, you wouldn't want to expand this out. You'd have no idea what's going on in that quadratic. This one's more of a reminder, just as we saw previously, the y and the x are actually independent to each other. So anytime you do a y transformation, it doesn't have any impact on your x stuff, and vice versa. And in this case, it's recommended that you're doing definitely DRT. Trying to do any other way around, we'll quickly see, is not impossible, but you'll double back on yourself multiple times. Okay, so here's an example I've got. Both of these are considered transformed functions. Step one, just make sure you have everything in its general form. So you wouldn't want to expand this one out. You would instead want to complete the square on this quadratic. That way, when you now look at both of these, I actually did this in the procedure way as opposed to the formula. Anyway, you can now directly compare these and say, yep, that's got a dilate of 3, that's got a dilate of 4, that's got different translations, that's got different translations. We can now see directly what's going on there. Now, what we're essentially going to do is apply a sequence of transformations to make the starting function look like the new function, starting with our dilations and then working our way down to translations. What does that actually look like? Well, if we have a look at we're starting from F and we're trying to go to G. If we look at the dilation difference between them, we're starting at a dilation of 3, we want to get a dilation of 4. So we need to figure out what number can I multiply 3 by to get it to look like 4. That's basically the only question you would ask yourself. And then we apply that to the function. So in this case, if you would multiply by 4 over 3, the 3's would cancel out, leaving you with a 4 in that spot. The thing to watch out for is you don't just stick it on the term you want to stick it on. Because it is a dilation that you're applying, it is a multiplication on the entire function. So your vertical translation, the other y transformation, is also going to be impacted by what you do here. This is why we do the dilations, the multiplications first, because if you start out with addition and then you multiply on top of that, you've now messed up your addition or subtraction. Whereas with addition and subtraction, that'll never change this, right? If I stick any plus or minus at the end of that, it's never going to change what's in the front here. So what we've essentially done is fixed our dilation. We now know that this factor of 4 over 3 is what we're going to have to apply to fix up our dilations. Next up, we look for reflections. There's none to be spoken of, so we move on to the final bit, which would be translations. So if we compare, you can do the x or y in any order. What did I do first? I did the y first. Okay. So we can see we're starting at 28 on 3, and we're trying to get it to 12. again, look, you're just trying to figure out what do I have to plus or minus to make one look like the other. In this case, if you were to add 8 on 3, that would in fact get you to 12. Nice and easy. If you plus at the end of the function, of the entire function, it only really impacts this spot here. Now, what's a little bit weirder to think about would be how do you fix the horizontal, or the x thing specifically. The way to think about it is you look at your x transformations. We're starting at x minus 1. We want to get to x minus 2. What we want to do is replace what's in the x spot such that it becomes the new thing you want it to become. So for instance, you have x minus 1, you want it to be x minus 2, so you replace this x with an additional x minus 1. Hang on, what am I saying? Did I write the wrong thing here? I did. Huh. That's supposed to say x minus 1 and then another minus 1. Unless I'm mistaking. Oh no, it is from f to g. No, we're starting at minus 2. We want to get to minus 1. You do have to plus 1. Yes, okay, I was looking at the wrong thing. We started here. We want to get to here. You replace the x with x plus 1. The plus 1 and the minus 2 will cancel down to now look like the minus 1. There we go. Almost stuffed it. And then we can see, like, we got our f looking exactly like our g. All we want to do from there is write down exactly what we did. So we started with that dilate factor. You can say along the y or from the x, however you prefer. Then we did a translation of 8 on 3 in the positive y, and then we did our translation of 1 in the negative x. So I know I put a lot of wording around that, but if you just look at like the raw math that was applied, yes, we had to do this whole transformation thing, the complete the square, but you would have had to do that anyway for the previous methods. We'll kind of ignore that as working out. If you look at the actual working out, it's just what do I have to multiply to get that? Simplify. What do I have to add to get that? Simplify. What do I have to add or subtract to get that? Simplify. So you can realistically do this in 3 steps as long as you're doing good mental math, which is a hell of a lot less steps and stuff than we had a look over here. So if you're up for that challenge, that approach is there for you. I'm more than happy for you to use it. Both approaches are written here. Anything to clarify about this or even the other one before we get into some questions? Cool. Okay, so this takes us, we're doing the Unit 3.4 version of this, that gets us to 3E. I have yet to update this. This is still kind of the Unit 1 and 2 stuff. So, yeah, if you're doing Unit 1 and 2, this is still also valid for you. Cool. Okay, let me see. Yeah, that's up. Let me grab the, no, I've lost it. Let me grab the class doc. This will detail all of the unique or grouped questions. Let me grab that. That should be in the chat now. I think I dropped the right one. Yeah, class 2. That's more so for like when you do homework later on if you want to practice specific questions. And I should probably drop a copy of these notes as well because we did look at a fair few. There's a fair few procedures to follow there, so it'd be good to be able to look at one immediately. So let me grab a copy of that. Yeah, okay, the PDF will also make its way into the chat. So we'll do at least the first one together, so I know we can all at least do one of them live with a bit of support, and then we can maybe take it and let you guys just see if you can take it all the way to the end. Okay. So the first question, 1a, we're trying to take the graph of y equals x cubed, and we want to get it to the graph of 2 bracket x minus 1 all cubed plus 3. That's our mission statement. We want to make that happen. We don't need the screen share anymore, so what I'll do is I'll pull up instead on the screen share the procedures that you could follow. I don't mind if we did the point form or the transformation by recognition. I'll leave that up to you guys. Who wants to start me off? Yeah, we can do both ways for practice. Sure. Okay, so let's yeah, I mean let's just do them in order then. So point form to start. Step one's nice and easy. It's pretty much just writing things the right way around.
Rewrite the y equals x cubed as f of x, or like as in that's function f.
Yeah, correct. So it's basically you have original functions f and new function g. The important thing would be whether you use xy or x dash y dash for it. So yeah, that one's going to stay as xy, and therefore, what are we going to do with the next one?
That's g of x, the other one.
Yep, that's g of x. So how do we specifically write it out?
Would it be g equals or?
I mean, like you could use f and g and just know that g is related to that. The problem is when you get to the x stuff, you won't know which is x dash and which is regular x. So my preference, again, this is pretty much just notation. It's just there so you know what's from what. F and G will help you with determining what y came from what. However, if you do your x dash y dash, that will also help you with the with knowing where your x's came from. So what we would specifically do would probably be something like this. So you have y dash x dash, and we know for certain that both x and y came from, well, where they came from, which functions. So yeah, that's just a bit of getting the terms right and writing things down. Step 2, what are we going to do?
You're gonna bring 3 to the other. You're gonna subtract 3 from both sides.
Yep, so you're talking about the y dash thing then. Cool. So y dash minus 3 is equal to 2 bracket x dash minus 1 all cubed. Sure. What else?
Divide both sides by 2.
By both sides by 2 is also good, yeah. I'll just do that here. And so yeah, why have you done that? What's the goal there?
We've got all like the transformations that can affect y on one side and all the transformations that affect x on the other side.
Yeah, exactly right. You want to get the y stuff on the y side, the x stuff on the x side. We didn't need to touch this one at all. There were no transformations on that. Nice. So that's what step 2 told us to do. Step 3. This is where things tend to have a few complications, so let's see how we go.
Do we equate like the? I mean, for the x side, we can just rip out x minus 1
Yeah,
and equal that to x.
perfect.
And well, y will be equal to y dash minus 3 on 2.
Yeah, that's exactly
And
right.
you can rearrange, and then that'll make you like you can figure out the transformations.
Yeah, that's right. So that's the part B of step 3, which is get the x dash y dash on its own. But yeah, fundamentally all we're doing is taking the left-hand sides, make them equal each other, and well, the right-hand sides and equaling them each other. Again, if you don't spot the transformations between them, you could just take the entire right-hand side, and it would just be a matter of cube rooting both sides, and you would get back to this anyway. But yeah, like you said, get x dash y dash on its own. So x dash equal to x plus 1, y dash is equal to 2y plus 3. Yeah, that's worked. Can I explain how I got to the x equals x dash minus 1? Oh, yeah. So did you write that before I had my explanation, or do you want me to touch it again?
Yeah, that would be good.
That would be good, as in you want me to explain it again?
Yeah.
So basically, we have our two end states for each of the functions. Once we've got everything on the y side stays on the y, and the x stays on the x, you now look at each of those individual portions. So the y side of the first one is the same as the y side of the second one. That's this. And the x side of the first is the same as the x side of the second. those, you put the equal sign between them. Yeah, you can rip the entire thing over. So for instance, if I were to rip the entire thing over, it would be the cubes in there, and then all I would have to do when I'm doing my rearranging is just make sure that I'm cube rooting both sides. We're just kind of skipping that a little bit because what you mainly actually care about are the transformations on both sides. That's the most important part. Clear enough where that came from?
Oh, is it just okay? So you just map the y equal to the y dash minus 3/2, and then the x cubed is equal to the x dash minus 1 cubed.
Yeah, that's right.
Okay,
look at
and
the
then
two.
just because it's simplified, you just cube root it.
Yeah, so so the next step is to make sure that you get the x dash and y dash on their own, and so yeah, part of that procedure would require you to cube root to actually achieve that.
Yep.
The other way to think of it is the important information in there is actually the transformation, not necessarily what the function was. So we don't really care this is a cubic, we just care that it was shifted. Well, we'll see what's happened to it, but we just care that the x has been like shifted by 1, for instance. And then yeah, the x dash y dash, that's just rearranging, right? Making x dash and y dash the subject of the equations. Anything further to clarify on those?
Would it be helpful to like factorize the y dash?
Yep. So if we're going to do exactly as I've written, step 4a would tell us to take any coefficients off of the x and the y, or in other words, factorizing. And so yeah, if we're going to do our TRD approach, we would now do wait, what have I done? Fix that up. 2 bracket y plus 3 on 2, and that would well yeah, that would allow us to now write in order translation, reflection, dilation. Cool. Okay. So as far as actually writing those out now, we're going to start with translations, then reflections if they exist, and then finally dilations. So with that in mind, how could we word the first sequence, or the first transformation in the sequence, rather?
Translate 1 unit in positive x direction.
Yep, that's it. Actually, yeah, that's probably something worth pointing out. If for those of us who weren't in the previous time we did this class, when you're looking at x dash y dash stuff, you don't do the whole reversal. Like this isn't a shift right by 1 anymore. The plus is. So plus is always what you expect it to be, versus when it's in a function, it sort of got its rearranging. So that's why that's actually valid there. Yeah. So translate 1 unit in the positive direction of the x. That looks like God knows what that is. Just shorthand. Translate 1 unit in the positive x direction. When you're writing it out, obviously write out the full thing. I'm just trying to not write out a lot of wording. Alright, so that's one translate down. Do we have another?
A vertical translation of 3 on 2 units in the positive y direction.
Yep, 3 on 2 in the positive y direction. Yeah, vertical translation, 3 on 2, positive y. That's exactly right. Cool. All right. There's only a max of 2 transformations for any given category. And so we know we've exhausted all our translations. Next would be reflections. Do we have any reflections? If so, what are they?
No reflections.
No reflections? How do we know?
There's no like negative signs on either of the like functions.
Yeah. So basically you're looking for any negatives directly on the x or directly on the y, or even this is where factorizing gets a bit weird. Factorizing could technically take it out, in which case, yeah, you're basically looking for any negative multipliers that would eventually make their way onto the y or the x term, of which there are none. So yes, no reflections. Last up would be dilations. Do we have any? And if so, what are they?
Is it a dilate by factor 2 from y-axis?
From what, sorry?
From the y-axis?
This is where the wording gets a bit weird.
Move
So,
x.
yeah, from the
It's
x.
along the y.
Yeah, along the y or from the x. So this is what I was sort of saying with when you got y in your mind, you say y, but you also say from. Yeah, you got to remember. So the way I always sort of picture it is imagining a dot on a xy axis. So we know a y dilation, the whole point of it is to stretch it that way. One way you could describe that is that it's getting away from the x, the point is getting further away from the x, or it's going further along the y. However you want to describe that is up to you. But yeah, the main point there was getting definitely the dilation factor of 2. This could be either from x or along y. And as I've said, from x would be what's written in the books, namely always using from rather than along, but I've seen some places that use along as well. That's it. We've touched on this term, this term, this term. We've done the full sequence. So if we have a look at like the amount of working out we did, this bit doesn't really count. You've got 1 line, 2 line, kind of like 3, 4, 5, and then your answer. So we'll see how it compares when we do the second approach. But I guess before that, is there anything I should clarify from this? Okay. Cool. All right, so I'm going to grab these again. So we had y equals x cubed, and we had y equals 2x minus 1 plus 3. Cubed plus 3. Cool. So as far as the other approach, let's see how we go. So step 1, do we even have to do anything here?
Don't think so.
Yeah, that's right. Unless you wanted to be a bit special and go, oh, you've got x minus 0 all cubed plus 0. Now you can see them. Haha. No, that's just painful. Why bother? Cool. Okay. Step 2 again is more of a reminder. So just keep in mind your y stuff will only ever affect the y, and your x stuff should only ever affect the x. So let's try to think about it. We're trying to go from here to here. What could we do to start it off?
Or you can see the dilation by factor 2.
Yep, nice and easy dilation. So we've got y equals 2x cubed. You multiply whatever the starting function is by whatever your dilation factor is. Cool. And you can maybe even, like, as you're doing your working out, you could write that it's a dilate of 2. In this case, what would this one be considered a dilate to along or from something? (50-50).
Positive 1 in x direction.
Oh, sure, you're moving to the next bit. Yeah, I was more so asking to clarify, like, what would I complete this as? Dilate factor of 2 from / along what?
Oh, okay. I mean, I guess I'll let someone else answer it.
Yeah, I mean, I'll write down the next one that you had, which was fine, and in the meantime, someone else can answer that. Or not. And we're going to finish that one off. Dilate 2 using similar wording from what we did before. Come on, risk it. Oh, here we go. From x / from x / along y. It's a multiplication on the function itself, and so yeah, that would be either from x or along y. Come on, guys, risk it. It's 50-50. Dilate 2 from x. Let's just use that. And then, yeah, like you said, so we could see that we started with x and we wanted to get it to x minus 1. We know from, just basic quadratics or even cubics that that would be a translate of 1 in the positive x. So we just write that. Translate of 1 unit in the positive x direction. Now, how you actually do that, because it's an x transformation, it only goes in the x spot. So it's not like you stick it out the end. That would be considered a y transformation. Any x goes in whatever the x spot is. And because it was cubed, it's got to go inside of that cube. All right, only one thing left to do here. Last one. We've done that, we've done that.
+3 in the y direction.
That's right. So because it is a plus in the y, or y specifically, it means we put that plus on the end of the function, whatever it is. And yeah, it's, you write that exactly as we wrote it. So that's translate 3 in the positive y. That's pretty much it. So, we've done this in more or less 3 lines of working out, keeping in mind we did have to do. Now this was an easier one, right? It's just, oh, that number is 2, I should say 2. That number is -1, I should do -1, right? Just looking directly at those is sort of whatever. It's more so when you start looking at both of them have transformations on them that you have to do slightly harder mental math. But yeah, that's what that procedure looks like. As long as you stick to doing dilate, reflect, translate in that order, you won't mess things up. Like just to sort of highlight that actually, let's say for instance I started with that +3. I now have y equals x cubed plus 3. If I then look at this and say, cool, I've got my +3, I want to now put this multiplier of 2 on there. To apply that multiplier of 2, it goes on the entire function. So now what that simplifies down to, you're going to get a +6 in there, and now to fix that up again, you now have to put an additional -3 in there to get it back to what you want, which isn't necessarily wrong, it just takes your 3-step transformation to a 4-step transformation or more.
What would the equation have looked like if it was a dilation of 2 from the y-axis?
Dilation of 2 from the y. With polynomials, it starts getting a bit weirder. Dilations from the y appear in this spot. So they're like a division on the x spot itself. The reason why it's weird with polynomials is that you can factorize that out, right? So let's say you had like a 2 here. That divide of 2 cubed can actually be brought out the front here. And so when it comes to polynomials, you pretty much never see this because it can be factored out and just combined into this term here. But yes, a dilate from the y or along the x would appear as a division on that specifically in, when it gets to the function. If we actually have a look at the screen share as well, you can see what the shortcut for that is. For any generic f of x along the x or from the y would look like that. It's a division by whatever the factor is. Yeah. This is the other reason I'll typically avoid using the f of x recognition stuff like this approach here, because suddenly you have to deal with the complications that x stuff is flipped, right? X translations, negative means right, positive means left, and dilations appear as divisions rather than multiplications. You've kind of got to get your head around those, which you kind of have to do anyway, but the less things that can go wrong, the better when it comes to, like, we're doing transformations. Probably to stick to the one you know best in transformations, and then leave a. Yeah, I mean, look, you can go either way with this. I'm just sort of going in circles on that. Yeah, that's the main approaches there. Whichever one you want to use is up to you. Anything to clarify as to how that's came about? Sweet. Okay. Still got a decent amount of time left. Let's see. So maybe I'll just sort of explain like what the rest of the chapter will look like. Question 1, you're starting from an initial like untransformed thing and you're getting to a newly transformed thing. The function that's actually there is going to be basically irrelevant because you're always going to follow the same, more or less the same procedure. This is the other way around. You start at transformed and end at untransformed. And I don't do it here. Is it Unit 1 and 2 that does it? Oh no, they've eventually got it. This one here, where you've now got transformations on both sides. Could have sworn they also did more. Maybe it's in here. Oh no, that one's just sketching. Is it in here? No? Okay. It's in Unit 1 and 2 then. So if you still have your Unit 1 and 2 book, if that's all you have, then that's in 7, D and E for the Unit 1 and 2 stuff. But we'll look at Unit 3, 4. So let's see if we can do a slightly different one. Sure, why not? Let's do question 2. Do you want to do it live again, like we just did? Or do you guys want to see if you can do one entirely yourselves? Independent? Sure. And I guess, yeah, if anyone wants to do a live one, I'll do it. And everyone else can just sort of like deafen and see, well, maybe not deafen, because then you won't know when to look again.
Just double checking we're doing 2A.
Yeah, 2A for this one.
One unit positive X direction and 6 units positive Y direction.
Quickly double check that. Or maybe
Oh,
just
it's the other way around. Sorry. 1 unit to the negative X direction and 6 units to the negative Y direction.
Yeah, that's better. Negative X and then also negative Y. Yeah. Some of these are easier, right? Like this one here. Even just looking at, we know quadratics, right? So we can look and see, okay, this one's here, this one's got to get here. The only thing that was happening at all was translations. If it was shifted right and now I want to get it back to the origin, I should shift it left. If it was shifted up by 6 and I want to get to the origin, I should shift it down by 6. So, some of those you can just sort of do by looking at them. As soon as dilation factors get in the mix, like for instance the part B, as soon as you get that dilation factor, suddenly that gets a slightly bit harder to do. But as you get more experience, you can just sort of look at these. You're basically doing it by recognition at that point. But yeah, what method did you use for that one, by the way?
First, I was thinking about doing 0.4, but I kind of messed it up, as you can see. Typically did recognition.
Yeah.
I think I did the other way around.
Oh, sure. Yeah. No. Yeah, I mean, like, one of the challenges with, like, the different methods is how you identify, like, X stuff, right? If you do it in one method, all positive is normal, right? Like, positive means right and up, and negative means left and down, versus the other way, if you're working purely with functions, your X stuff is flipped. So being able to Yeah, there's pros and cons to both. But okay, cool. So that's that. Now we can jump onto one that's got a bit more involved.
What was the answer for 2A again?
Yes, that would be a shift. Let me get it right. Shift left by 1 and a shift down by 6. Because you want to take this thing that has a turning point of 1, 6, and you want to shift it down to the origin. Is another way of thinking about it. Fair enough. You can write those in any order, by the way. So you can say the x first and then the y, or the y first and the x. Either way is fine. Let's see. See, here's where like they can apply a dilation factor. This one's super sneaky though, actually, so maybe we'll do it. Because, well, I guess we'll see who remembers exactly what I said about these dilation factors. Let's have a stab at 2e on this one. I might have to actually do this one myself just to make sure, because there's so many ways you can do it.
Chris, will it be like 1 unit to the negative x direction?
I'll get the full list just because there's a few ways this could be valid. Let me just get
Yeah,
the full list.
Yeah, I was about to go on with that. 3 units in the positive y direction.
Yep.
Dilate by factor 2 from y axis.
Dilate 2 from y. Okay, let's see. Can that work? So you've done shift left 1, shift up 3, y shift up 3. Did you try...
Sorry, shift down 3, did I say?
Shift down 3, okay. Shift down 3. Okay, still, where might that 3 have come from? started with that. I'm going to see if we can do that. When you wrote out your function, did you have this multiplier of 2 on the outside?
Yes, that's
Okay,
a
cool.
mistake.
So just a bit of algebra issue there then.
Would it
Oh,
would
yeah.
it be down by 6 or?
Yeah, so if you would follow through this procedure, the next one seems like it should be a down by 6. Yeah. I'll double check them all at the end, but seems good so far. And then after you're down by 6,
What makes it a translation of 1 in the negative x direction rather than a half? Just looking at
yeah.
that x dash up there.
So depending on, this is what I'm trying to get, because like this is what I had. If you follow exactly what I've written for the x dash y dash stuff, you do get the minus a half, the plus 6, and the dilate of 2 from y. What I'm trying to figure out is, because you can write it this way instead, the order can change and the numbers will change with it. So I do think, looking at it now, you have pointed out something, yeah, which is because this was done in T, well, T, T, and D, technically, this should be a half, but that was also sort of an algebra mistake when he went through it. He had this 2 out the front here, which would have changed what he wrote. So
Yeah, because what I had was, because if you have the 2x minus 1, and then you kind of factorize it, you get 2 at the front of the brackets, and then inside the brackets you have x minus a half. So then that's how you get the isolate the dilation factor of 2,
Mhm.
but then also you know that it's moving by 1/2.
Yeah, that's right. So if you do that approach as described with the TRD stuff, then yeah, you would get minus a half plus 6 and then the dilate of 2. The reason why you can get a different order is, for instance, if you leave this here, you would now say the dilate of 2, there's no more dilates, and then you can do your translate of the 6 in the y, and the translate of, in this case, it'd be minus 1 in the x. So yeah, it looks like this could have been good if dilate was said first, but otherwise, yeah. This is the trickiest part of this thing. You can do many different ways of of writing the same sequence. It's kind of funny to think about that, like why are there multiple ways of achieving things? I used to do a little demo, which was like, cool, I got this point, I want to put it here. What can I do? Well, maybe I could reflect it and then reflect it. That's one way of doing it. Maybe I could even do the same thing with translations. Right? I translate this way and then this way. I could multiply, well, maybe not multiply it because we're assuming they're in the same sort of spot. But like the point is, there's multiple paths to get from one spot to another. So all of these are valid. And I'll just sort of briefly touch on again, the way the assessors handle this is they'll give you that, and they'll say, hey, the first one on the list is a dilate of 2. Now you can't really do the translate stuff first. You now have to keep it in the expanded form. So that's why it's kind of good to know when you're doing your x dash y dash anyway. It's good to know both ways of doing this, whether you expand or factorize, and what that actually means for how you write out your final answer. I don't think I'll be able to find. There was one exam that I've got in my mind that they did exactly this, but you know, there's many that I could pull from, and I don't know exactly what the year was. So, if you're interested, I think in the actual classroom tab, there are a bunch of work solutions to exams. If you want to go digging for it, feel free, but otherwise you can just sort of take my word that they give you the first one and they force you to get the next couple. Yeah, that's really about it. I can give you back a minute in your life, or I can answer any final questions that anyone has.
If your teachers prefer you using the order of DRT, would you be marked down for doing it in the other order?
I mean, I would hope not, because then your teacher's doing a bit of shady stuff. But, I mean, look, at that point, if you know your teacher prefers one thing, then do what your teacher prefers. They are marking your sacks, after all. They should mark you down. It is perfectly valid to do it one way or the other. But yeah, there's a bit of human error in there, depending on how much of an ego your teacher may or may not have. So just be mindful of the human factor there, I suppose. In the exam, that won't matter. All of this is valid in the exam. Cool. I mean, I'll stick around for any more questions until everyone leaves, upon which I will go, I don't know, have dinner or something. Enjoy the rest of your days.
Thank you.
Thank you.
I thought I'd turn my camera on for the
Hey,
first time in
first time
class.
ever. Look at that.
Yeah. Yeah, honestly, like, I just wanted to talk about, like, what's popped off.
Hmm.
I'm not really sure how long this might go for. It really, like, it's like term by term. So first, I'm going to be playing for 10 weeks, and then depends if I do good, they might, like, ask me to come for 10 weeks more.
Mhm.
And it could go for, like, that much. Maybe, I know, like, I think the very last of that might be, like, October or November. I'm not sure.
Yeah, right.
So yeah, we'll see how it goes. But like,
No, that'll be sick either way. It'll be a good experience for you to have.
yeah, I mean, either way, like, I'm like really happy. I'm really like grateful for like the opportunity you gave me, like all these like months. I think like I learned like pretty well, like from you.
Yeah, no, I
Still
can
make
see for sure. Like,
still make a lot of mistakes, but that's okay. No,
well, you
but
got
like
time to fix
genuinely,
them, right? So I guess, like, I know that you're doing your thing, but you are gonna need to practice these things at some point. Obviously, you might
yeah,
not be able to attend the classes, but uh, try not to let it be the entirety of your life. You did, in fact, well, spend basically a full year doing this. It'd be a shame to have the skills weaken over time, but I'm sure you'll keep up with that stuff. I'm
yeah.
sure.
I mean, it's a lot easier now because I'm also doing methods at school.
Hmm.
And I found that like we just had our first test and I scored it in the top of my class. So
Yeah.
I mean, yeah, I
Nice.
feel like yeah, even though like I probably can work on rectifying silly mistakes, I think it's really helped me like this class and really like
I appreciate
grateful for
that.
that.
It's awesome to hear. And yeah,
Yeah.
like you're at for a while, you've been at a stage where you can self-correct now. Because when you have these silly mistake stuff, it really is just grinding through these questions over and over and over again until it's just like you just can't make the mistakes.
Yeah.
And you'll see me occasionally slip up in the class, and that's me teaching it as well. One of the things, I think even just me teaching this has made me better at methods as well. And so maybe, I don't know if you have like an opportunity, probably not. Even if you have like your friends and stuff, teaching them the concepts will doubly reinforce it for yourself as well. It puts an additional layer of pressure on you getting it right, because if it's just for yourself, it's like, yeah, okay, I'm getting it wrong, but I made that mistake. Versus, oh shit, I taught someone else the wrong thing, and now they've got
Yeah.
it wrong because of me. Oh no.
Yeah, for sure.
So
Yeah.
yeah, if you can, for whatever reason, maybe like help out your friends with this sort of stuff as well. They don't need to join this. They can, they can learn from you.
No, I mean, if I've ever got anyone looking for some sort of like method tuition, I definitely recommend you.
Love to hear it.
I've honestly like my feedback is like I really enjoyed like the exam revision that term. Like I feel like that gave me like the most benefit because um obviously the hard questions you would go through it, but it sort of gave us like a chance to like understand how methods questions are written, especially for me. Because I know like I think Pia was already in year 12 last year, so she probably would have been like used to how it works.
Yeah,
So
for
yeah,
sure.
I'd say like that really helped me last year. And it, like helped me like apply all the concept that we'd learned throughout like last year.
Yeah, that'll definitely be like we pretty much try to get there as fast as possible in these, because that is fundamentally what you will be doing in both the SAC and the exam scenario. Because yeah, like we've got all the I mean all the lessons are pre-recorded at this point, right? Like you could go and watch all the 15-minute things that I've done for them, and we could be focusing purely on exam revision stuff. But I mean, like you see in the classes, right? A lot of people just need to get the fundamentals down, and then you can now use that to apply to the other things, which is why it kind of has to be later on in the year, or at least
Yeah, of
closer to
course.
SAC
Yeah.
times.
Yeah,
Um,
right.
but yeah, like we do try to, like I won't cover the easy stuff here. Like you never see me touch linear, more or less, right? Or if we have, it'll be like speed run the entire linear in an hour.
Yeah, similar to like what we did with polynomials like last
Yeah,
week, I guess.
yeah, like polynomials. That has a few complexities around it, but basically the things that are typically easy you just won't really see here, and we'll spend a lot more time on the what is it, the counting method stuff.
Yeah.
Transformations gets people a lot, and those are the main ones, I think. Composite functions, one very small section. Composite functions is what people get got by. But yeah, cool. So I'll see you when I see you next, I suppose.
Yeah, I
And
guess
yeah,
so.
I guess just even keep me updated with how you've been going. I'll be curious to
Yeah,
hear about
yeah,
that.
for sure, yeah.
It's
I'm
awesome.
just gonna be like, I guess I'm gonna try and like do what I did with methods last year, but this year I'm going to have to do a special as well. So
Yeah.
yeah,
Yeah. I mean, look, like the fundamentals of methods will prepare you for special as well. I kind of touched on a few special related stuff in here as well when the complex numbers come up.
yeah.
But obviously it's a big difference. Do you already have all your special stuff bought, even up until year 12?
As in like textbooks?
Yeah.
I mean, I've got the online ones.
You
Like,
got okay, you do. Yeah.
yeah,
I was gonna drop it off if you didn't already have it, but yeah.
yeah.
Sick. All right. Well, cool. Yeah. As I said,
Cool.
keep me
Yeah,
posted, just in general life stuff as well, just because that's
yeah,
also curious to hear.
for sure. Yeah,
And yeah, when I
yeah.
see you
Thank you
next,
so
I'll see you
much.
next.
Yeah, keep in touch. Thank you.
Thanks, mate.